Hello, game theorists. Today we are still in Chapter 7, looking at games with mixed strategies. So, as you know by now, a mixed strategy just means that the players randomize. So it turns out that there are some cases in which a mixed strategy with a randomization can dominate a pure strategy. That lets you eliminate that pure strategy has been dominated, and that can simplify your analysis. As you'll come to appreciate in the next several episodes, analyzing games that are 3 by 3 or larger can be pretty complicated. Therefore, if you have the opportunity to eliminate a dominated strategy and make your life easier, you'll definitely want to take advantage of it. So this is an important skill that can really save you some time when you're analyzing these more sophisticated games. So here's an example game. My players are unimaginatively named row and column. Column can play left or right. Row can play up, middle, or down. So our first job is to look to see if any pure strategies are strictly dominated by another pure strategy. If so, we can eliminate them. Next, we can do our best response analysis and search for Nash equilibrium. So to get some hands-on practice, go ahead and pause the video here while you think about that. When you think you have the answer, press play and we'll see if you're right. Alright, so it turns out that none of the pure strategies dominate any of the others. So, start at the row player. It looks like up is better than middle and down if we know column is playing left. Unfortunately though, up is not so great if they're playing right, so up is not going to dominate anything. So middle and down are worse than up if column is playing left, so none of these strategies dominate up, and up doesn't dominate anything. Let's look at things from column's perspective. Column players' payoffs always come second, so they care about these numbers over here. So against up, they'd rather play right and get 4, but then against middle, it's better to play left. So there's no single strategy that's always better. Nothing is strictly dominated by another pure strategy. So now we'll do our best response analysis. So if column is playing left, row's best response is to play up and get 10. That's better than getting 0, better than getting 1. If column is playing right, row's best response is to play middle, because that gets 7. Getting 7 is better than getting 1, and it's also better than getting 2. Now let's do it the other way. If row is playing up, column's best response is to play right and get 4. That's preferable to playing left and getting only 3. Best response to middle is left because that gets you 5. Right only gets you 1. If row is playing down, then both left and right are best responses because they both get the same payoff of 0. So you do our best response analysis, you realize that there's no pure strategy Nash equilibrium. So none of these cells here have both payoffs underlined. So there is a Nash equilibrium, but that Nash equilibrium is going to involve mixed strategies, not pure strategies. So we couldn't eliminate anything with the tools we had earlier. However, now we're going to develop a new tool and look at dominance by a mixed strategy. So here's when you want to have your eyes open for that. If you look at our game here, you realize that down is never a best response. So if column plays left, you wouldn't want to play down, you want to play up instead. If column plays right, you still don't want to play down, you want to play middle. So down is never a best response. That suggests that down might be dominated. Keyword here is might. So in the past, some of my students have just assumed that because it's never a best response, you can just get rid of it. That's actually not always true. We'll see some examples later on that prove that point. So because down's never a best response, you should be suspicious. Don't get rid of it entirely right away. You gotta do some work first to verify it, but it does alert you that down could possibly be dominated. So we gotta do some verification to double check, and I'll show you how to do that. So here's why I have to verify. I'll show you another game that we'll analyze in greater depth later on. So here we have row and column again, and here we have strategies A, B, X, Y, and Z. Let's do our best response. So if row is playing A, column wants to play Y because column gets them Y wants to gets them 10, whereas X gets them just 0, and Z gets them 9. If row is playing B, column's best response is to play X. X gets them 10, whereas Y and Z gives them 0, 9, and both of those are worse. So Z is never a best response. You look at the best response analysis for row. So if column is playing X, row would prefer to play A and get 10. That's why I got an underline. That's better than getting 0 from B. Likewise, if we know that Y is going to be played, it's better to play B and get 10 than play A and get 0. Against Z, you'd rather play A and get 7. That's better than getting 5. So Z is never best response, so that should make you suspicious if Z could potentially be eliminated. However, just think about it kind of just humanly without your game theory background. Z does seem like a reasonable choice. If you play X or Y, you might get 10, but then you also might get 0. There's some risk there. If I play Z, I always get 9. That's a pretty good and pretty safe option. So you can see why someone might play Z even though it's never a best response. Turns out our human intuition does have some foundations in game theory. Though Z is never a best response, you can't actually eliminate it. And there's an equilibrium where we play Z some of the time. It's part of our randomization mixture. So we'll prove that all later on. I'm just showing you, just arguing that you can't eliminate a strategy solely because it's never a best response. You got to do some more work to prove that you can eliminate and to prove that it is dominated. So you're probably curious now, how do we actually prove it? I'm glad you asked, because that's our very next topic. So let's go back to the game we had originally. So we had this game, and we were suspicious because down was never best response. That made us think that it could potentially be eliminated. So now we're going to add a mixed strategy to our table. So maybe row could play up half the time, and they could play middle the other half of the time. So we got to calculate what the expected payoffs are for both players, and that can help us fill in our table here. So to get some more hands-on practice, go ahead and calculate those expected values. Pause the video here while you're doing that. When you think you have the answer, press play, and then we'll figure out if you're right or not. Okay, I'll assume you've given that some thought. Let's go work through those expected values. So let's work on this one here. Let's try to figure out what is row's expected payoff if column is playing left. So with our mixture, we're playing up half the time. If we play up against left, we get a payoff of 10. So we're getting a payoff of 10 with probability 0.5 half the time. The other part of our mixture is that we're playing middle half the time. Now if we're playing middle and Colin is playing left, our payoff is going to be 0. So you're getting a payoff of 0 with probability 0.5, so you have 0 times 0.5. Let's just finish up what that expected value is. We had 10 with probability 0.5, so 10 times 0.5 is 5. We also get 0 times 0.5, but that's just 0. 5 plus 0 is 5. So here's what we've established. We're saying that if we play this mixture, then our expected payoff is going to be 5 if Com is playing L. So we put a 5 for that payoff over here. So let's go fill it in. So that's the first part. Now let's go fill in the rest of the table. So we play this mixed strategy. We play up half the time and we play middle the other half of the time. It's possible that Colin plays right instead of left. So now we gotta find what's our expected payoff against right. So half the time we're playing up. If we're playing up and they're playing right, we're getting a payoff of 1. So you get 1 with probability 0.5. The other possibility is that we play middle because we play middle half the time. When we play middle against right, that means our payoff is going to be 7. We do that half the time, so we have 0.5 times 7. That's also part of our expected payoff. Let's put all that together. We have 1 times a 0.5. We get a payoff of 1 half the time. 1 times 0.5 is 0.5. We get 7 half the time. 7 times 0.5 is 3.5. 0.5 and 3.5 equals 4. So what does all that mean? It means that if they're playing right, then we're getting a payoff of 4 in expected value. So you want to replace that question mark with a 4. So you might also be curious about what the expected payoffs are for Colin player. It turns out that for this particular exercise, we don't have to worry about that. Why am I unconcerned about Colin's payoffs? Take a step back and try to figure out what are we ultimately trying to do here. Remember, what we're trying to do is see if we can eliminate D. We were suspicious of D because D was never a best response, so that made us think we might be able to get rid of D. So there might be some mixed strategy that could eliminate D. So to figure out if a strategy dominates D, we also have to figure out the row player's payoffs. So the column player's payoffs are not relevant to whether this mixture dominates D. So you just save yourself some work and not worry about those, because all that needs to happen is the mixture has to be better than D for the row player. And it turns out the mixture is indeed better. So if column is playing left, I'd rather play as mixture and get 5 than play D and get 1. Also, if column is playing right, I'd rather play the mixture and get 4 than play down and get 2. So the mixture strictly dominates D. We have dominance by a mixed strategy. We know from earlier that if a strategy is strictly dominated, you can get rid of it because a strictly dominated strategy is never part of a Nash equilibrium. So you just cross out D in your table. So once you chop out D, the game looks like this. You have a 2x2 game. How do you analyze that? Well, you actually already know that. We talked about that in the first couple of videos in this series in Chapter 7. So you've already got all the tools you need to take care of this game. Possible question from the audience. So I told you that the mixed strategy involved play U half the time, play M the other half of the time. I gave you the probabilities. Now what if you're looking at some game and you don't know in advance what the probabilities are? How do you deal with that? So here's the method. Let's just say more generally, you're playing U with probability P and you're playing M with probability 1 minus P. If you just guessed different probabilities like 0.5, 0.5, you might get lucky and find one that works. But if you're not lucky, you could be guessing a lot and doing a lot of checking and wasting a lot of time, and this ends up hurting you. So you want to take this more general approach instead. So we're still suspicious that D could be dominated, so we just say in general, we play with probability P and M with probability 1 minus P. Now let's try to find a value of P that's going to work. So we go and fill in the expected values. So we got this mixed strategy added to our table. We'll first think about what do we do, what's our expected payoff if column is playing left. So if column plays left and we're playing this mixture, here's what happens. With probability P, we play U. When we play U, we get a payoff of 10. So we get 10 with probability P, so an expected value, we get 10 times P. The other part of the story is that we play M with probability 1 minus P. When we play M, we get a payoff of 0. That means the likelihood of getting at 0 is 1 minus P. So to get the expected value, you multiply 0 by 1 minus P. 0 times 1 minus P is just 0. So to finish off the calculation, you get 10P plus 0. That's going to be 10P. So 10P is going to be our expected payoff if we're playing this mixture and column replies with left. So that goes right over here. The next part is to figure out what is our expected payoff from the mixture if column plays right. So our mixture means we play U with probability P. So with probability P, we're in this row. And we do that, and they're playing right, we get a payoff of 1. We're getting 1 with probability P, so that means we get 1 times P in expected value. Now let's look at the other part. We're playing M with probability 1 minus P. Whenever we play M and they're playing R, we're going to get 7. We get 7 with probability 1 minus P, so we're getting 7 times 1 minus P. So just go and expand this whole expected value. You're getting 1 times p, which is just p, plus 7 minus 7p. So you get a p minus 7p, that's a minus 6p, and you still have this positive 7. So in this case, if they're playing right and you're playing the mixture, your expected payoff is 7 minus 6p. So that's going to go over here in the table. So you just filled in that value over there. So you got both of our expected values plugged in. The next step is to figure out if the mixture is going to dominate the pure strategy D. So once again, you don't need to know columns payoffs over here. These question marks can remain as question marks. That's because to figure out if one strategy dominates another strategy, you just have to know if Rho's payoffs are bigger. We've got Rho's payoffs, so that's all the information that we need. So when are these payoffs from the mixture bigger than the payoffs from D? Two things have to be true. So the payoff, if they play left, for the mixture has to be bigger than what we get from playing down. So we have to have 10p being bigger than 1. If 10p is bigger than 1, that means the mixture is better against left. We also need 7 minus 6p to be greater than 2. If 7 minus 6p is greater than 2, what that means is that the mixture is also better if they play right. So you need both of those to be satisfied. So these two inequalities here, we only have one variable. You're not guaranteed in advance that this will work out. So like you know from algebra, if you have two equations and two unknowns, you can normally solve that. Here you've got one unknown but two inequalities, so a solution is not guaranteed. That's why you've got to verify. You can't just assume the mixture is better, you got to actually check it. So can we find a value of p that makes both of these work? Let's do some rearranging. So if I have 10p greater than 1, I can just divide both sides by 10. And that's saying that I have to have p bigger than 1/10. The other part is that I had to have 7 minus 6p greater than 2. 7 minus 6p greater than 2. I can also rearrange that. So I'll put the 2 on the other side here. 7 minus 2 is 5. That means I get 5 minus 6p has to be greater than 0. The next thing I'll do is move that 6p to the other side. So I have p's on one side, I have numbers on the other. That gives me 5 greater than 6p. Very last step, divide both sides by 6, and I find that 5/6 has to be greater than p. So if I'm putting all that together, it means that the mixture is going to dominate D if p is bigger than 1/10 and at the same time p is less than 5/6. So if I can find a value for p in that range, that means I can get rid of D. It means D is strictly dominated. So you can think of many numbers that satisfy that condition, one of which is p equals 0.5. 0.5 is bigger than 1/10, and 0.5 is also less than 5/6. That's how I knew way back over here way back over here that 0.5 would dominate D. So if someone is not telling you in advance what mixture to use, you just follow this procedure here and find a mixture that works. So here's the basic outline. You first do your best response analysis. When you do that, you might find a strategy that's never a best response. Some strategy like D in our game that is never a best response. When you see something that's never a best response, get suspicious. Start thinking there might be some mixture that might eliminate it. So you make your mixture just very general. You play one strategy with probability P, and you play the other strategy with probability 1 minus P. Then go ahead and take your expected values. Once you have that, see if you can find a value for P that's going to get rid of D, or get rid of that strategy you were suspicious of. That's how you can deal with these games and potentially eliminate a strategy. If you can get rid of a strategy, that makes your analysis easier. So that wraps up that example. Be sure to tune in for our next episode in which we'll go through another example.